the camera.
You can see yourself whether you're on the camera.
Oh, but then I'm gonna take up like half of the camera.
Well, while you're announcing.
Okay. Oh, this is awkward.
There,
That's
then
right.
there,
No, close, come this way. Now turn and face them.
face.
But what about all these?
They see you up there.
Yeah, I'm just gonna, this is really weird.
Right?
And it was all recorded, so. Okay, are we ready to begin? Welcome back again. I'm very happy to announce my academic sibling, Gage, will be speaking on annular links, double branch covers, and annular Khovanov homology. Thanks for coming, Gage.
Yeah, thank you, Melissa. And before I get started, I did just want to say thanks to all the organizers for the chance to speak. And it's really nice to, even though I wish I could be there in person, it is nice to have the remote option to still be able to participate. And I should say that some of what I'll be talking about today is joint work with Fraser Binns, who's another graduate student at Boston College. And he might be applying to jobs next year, or if not, definitely the year after that. And also, before I start talking about math, I did just want to take a little bit of time to mention that I'm currently speaking on the stolen territory of the Massachusetts people. And I just think it's important to take a little bit of time regularly to be thinking about that as like a small way of thinking about the continuing history of colonialism and genocide here in the US. But with that being said, maybe I'll tell you about some math too. So there's like a few words in the title of my talk, and one of the first things that came up was an annular link. And these are just a link where you're embedding circles into a thickened annulus. And you, again, like any link, you're thinking about it up to isotopy. And if you really like thinking about links in S3, instead, you can think about an annular link as like a link with one extra component in S3, but that extra component is like a special distinguished unknot that you picked out from your link. And right, like you get this equivalence by thinking about the thickened annulus as the complement of that unknot. But a picture is worth 1,000 words. So here is like a nice picture of an annular link. And if you wanted to see that unknot in S3, it would be the meridian of this thickened annulus that I'm drawing here in red for you. So this is either just like a one component annular link in the thickened annulus, or you can think about it as this two component link in S3 with that extra red component, but it's kind of a special component. And one way to produce lots of annular links is by taking braids. Here's another nice picture. Braids are things where we're like taking our strands and they run from the top of the page to the bottom, but never loop back around. And if you wanted to build an annular link from a braid, you can take the closure of the braid. And we know we could build any link in S3 by taking closures of braids. And if you wanted to instead be building an annular link, you just kind of remember where you're closing up around, so that you kind of just remember this braid axis that I'm drawing in red. And so that now it's like very naturally an annular link. And this is one nice family of annular links that you might be interested in. And so part of my talk, my title was saying something about annular links and double branch covers. So maybe let me tell you like a little story here. And I think this is something that I think is just a really nice perspective on how to study annular links or how to study braid closures in general. And so this is something kind of a big theme I think of to myself when I think about this talk, is kind of this sort of picture right here. And so just as like a background and reminder, if you have a link in the 3-sphere, there's like this really nice way you can build a 3-manifold from this link by taking its double branched cover. And as we all kind of know, this is a pretty fruitful way of studying links in S3 by taking it, building a nice 3-manifold that you can associate with it, and then studying that 3-manifold. And you unlock all sorts of techniques from 3-manifold topology this way. And you can also do this in the thickened annulus as well. And so actually you get a little bit more because you're working in a thickened annulus. All of a sudden you actually have built yourself a 3-manifold with a link inside of it. And how does that work? I think there's a few ways to think about this. The simplest way to write down is your link in the thickened annulus. You could think of as a link together with that distinguished annular axis, this unknot. And so you can take the branch double cover of that link, and that's a 3-manifold. And then you just look at the preimage of this annular axis in the branch double cover, and that will be either a knot or a 2-component link. And so now again, you have this nice way of associating some other object to your annular link. And so it might give you new tools you could use to study your annular link. And I should say specifically, if you started with a braid closure, then this link that you'll build is actually a fibered link. And it's nice in some other ways that like the braid would be related in a really concrete way to the monodromy of that fibered link. So you actually understand quite a lot about this fibered link you've built if you started with a braid closure. But even if you don't start with a braid closure, you're building some link in some 3-manifold. And so we have lots of tools to study links in 3-manifold. So now you can use any of those tools you like to maybe hopefully study annular links. And I guess I should also just say, if it's something that's familiar to you, like as a nice connection, this is maybe like a 3-dimensional version of it is a 3-dimensional version of like the Berman-Hilden correspondence for braids and mapping class groups. So the final part of my title is Annular Khovanov homology, and that's a tool I quite like to study annular links with. And it was introduced in 2004 by Asahida, Shizutsuki, and Sakura, and it's a categorification of the Kaufman-Skane bracket, which you can think of as maybe an annular version of the Jones polynomial. So just like Khovanov homology in S3 is some generalization of the Jones polynomial, this is also generalizing some polynomial. And if you take the right kind of Euler characteristic, you'll recover that underlying polynomial. And specifically, annular Khovanov homology is like some triply graded vector space with a homological quantum and annular grading. So that means for any triple of numbers, you get some vector space back, given starting with some link. And there's like a way you could forget about the annular grading in some way and get just Khovanov homology in S3. And I guess for experts, I just mean that there's a spectral sequence relating these. But I think those are kind of some of the basics to know about annular Khovanov homology. And we can see an example too. So this is the braid closure we saw before. It's this braid closure sigma 1, sigma 2, sigma 3. And I've written down its annular Khovanov homology for you. So first over F2, it's 1-dimensional for these 8 triple gradings, and it's 0 in all other triple gradings. But that's just kind of the sort of thing you can have in mind for what the annular Khovanov homology of something might look like. It's just going to be giving you a triply graded vector space like this. And then as a second example, like here is our first example of an annular link, and I've computed its annular Khovanov homology for you over C this time. And again, you can see it's 2-dimensional in one trigrading, and then it's 1-dimensional in some other trigrading. And then I think a really natural question is like, that's all well and good. Like I just told you that the invariant is this for some things, but you might want to know like, oh, well, kind of what does it mean that this is what the annular Khovanov homology of this annular link is, or that this is the annular Khovanov homology of this braid closure. And you know, as a topologist, I think it's just kind of natural to be wondering like, well, what sort of information is this really telling me? And we know some things here. So there's work of Grigsby and me, and more recent work of Ji and Zhang that shows that annular Khovanov homology detects braid closures, and it detects braid closures just by looking at the highest non-zero annular grading. And if it's one-dimensional, then it's a braid closure, and if it's not one-dimensional, it's not a braid closure. So going back, I know we already knew this was a braid closure because I told you like what we started with, but we can see that just from its annular Khovanov homology, because this highest non-zero annular grading, the K grading here is 4, and it's just one-dimensional in this grading. So we know we must have started with a braid closure just by looking at its annular Khovanov homology. And kind of conversely, looking at this picture, like this doesn't look like a braid closure, but you know, maybe there's some clever way we could move it around so it is actually a braid closure. And then annular Khovanov homology actually tells us that's not possible. If we look here, the highest non-zero annular grading is 2. And we see that here the annular Khovanov homology is 2-dimensional in this highest annular grading. So we know it's not a braid closure. But then there's other things we know. So work of Baldwin and Grigsby showed that annular Khovanov homology detects the trivial braid. And then later, Grigsby, Anthony, Licata, and Verley show that annular Khovanov homology actually detects every single 2-braid closure. And they do this really, it's very computational. They just compute the annular Khovanov homology of every 2-braid. And then combining that with the fact that we know annular Khovanov homology would tell you if you are a 2-braid, you can just check that all of these are different. And right, it's not too hard to, well, I mean, you still have to figure out how to compute it, but it's not too hard to write down what all the 2-braids are because you only have 2 strands. So you're just like choosing how many times you twist those strands together. And so they just compute the annular Khovanov homology of all these 2-braids, and they're like, oh, they're all different. So that means annular Khovanov homology detects all of them. And then more recently, like Fraser and myself showed annular Khovanov homology detects the 3-braid sigma 1, sigma 2, and sigma 1, sigma 2 inverse, along with the 4-braid sigma 1, sigma 2, sigma 3. And we can also show annular Khovanov homology detects this 6-braid sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. And then since then, using the same ideas, Farber, Reynoso, and Wang were able to show that annular Khovanov homology detects this 5-braid sigma 1, sigma 2, sigma 3, sigma 4. And then Fraser and Day were able to show annular Khovanov homology detects this 8-braid and this 10-braid. And I'll spare you from reading out all of those. And I should just say, like, these results here are really using the same strategy that Fraser and I were using as well, and that we'll see a sketch of a proof of. And so all of these are kind of building on the same idea. And it maybe will become clear, but I'll point out like what was extra that they needed that we weren't able to do originally too. Right, and so I think so far in the talk, I've told you about annular links, and then I told you a bit about this nice invariant of annular links that I like, annular Khovanov homology, but I also told you something about branch covers, and so you might kind of wonder, like, is there some sort of connection going on here? And it turns out that annular Khovanov homology fits really nicely into this story about studying links in this way by building branch double covers and taking lifts inside of them. So just as a reminder, if we have our annular link, we were building this 3-manifold by taking its branch double cover and then looking at the preimage of the annular axis, we get a link inside of there. And it turns out that there's this nice relationship between the annular Khovanov homology of the link you started with and the knot floor homology of this link you've ended with inside of the 3 manifold. And again, when I say nice relationship for the experts, I mean there's a spectral sequence. And this appears in work of Lawrence Roberts and Grigsby Bailey in 2007 and 2009. And so this is going to maybe let you translate information about annular Khovanov homology into information about knot floor homology, at least in some cases. Or at least that might be what you hope it lets you do. And you might kind of just wonder, like, well, why would translating from annular Khovanov homology to knot floor homology be useful? And there's kind of general reasons why it might be useful. And so, like, you know, the hand wavy reason is just this general reason that, like, well, we know that often topological applications of Khovanov homology use some relationship with the floor theory, so maybe this might be useful. I think, you know, a very good example would be something like Kronheim and Mrfka, where they're able to show Khovanov homology detects the unknot by relating Khovanov homology with an instanton floor homology. But there's lots of other examples like this, where people are able to prove something about Khovanov homology by using a relationship with floor theory and then using all sorts of tools that we have in floor theories. But more specifically, looking at, like, you might think, going back to this list I gave you, like, why might it be helpful to prove something about detecting some of these braids specifically? And so I should just say, for the next little bit, I'll focus specifically on this 4 braid, sigma 1, sigma 2, sigma 3. But the ideas of the proof will basically be the same for all of them, and I'll point out, like, anywhere where you need to do something different. So you might ask, like, why these ones specifically? And so just going back, if we focus in on that 4 braid, sigma 1, sigma 2, sigma 3, if we trace through what happens when we take its branch double cover and then lift the braid axis up into the branch double cover to get a link, well, we know that this is a braid that represents the unknot, so its branch double cover is S3. And then if you trace through the construction of what's happening, the link you've built inside of S3 ends up being this torus link T24. That might not be completely obvious, like, but it isn't hard for you to sit down and check that if you wanted to later. So it's not, but don't feel like it's like something you're missing if it doesn't seem like immediately obvious to you either. And that's specifically useful because Fraser and I also had shown that knot floor homology detects the torus link T24. Right, and so I guess those other names that I put there, where it was Farber, Reynoso, and Wang, the braid they were thinking about gives you the torus knot T25, and so they were able to prove this thing about annular Khovanov homology after they did all this hard work to show that knot floor homology detects T25. And then again, like with those braids I wrote down that Fraser and Subankar Day were able to show annular Khovanov homology detects. Again, it's like they do all this hard work to show knot floor homology detects the corresponding torus link, and then like this sort of result kind of comes along using these ideas that I'm about to show you. So that's why Fraser and I weren't able to show that right away, is these people needed to do lots of hard work on the knot floor homology side. But then once you know that knot floor homology detects something, they're able to kind of use our ideas pretty easily. So I'll give you like a nice sketch of how we show that this 4 braids detected using the fact that knot floor homology detects this torus link T24. So if you start with some link and you're just assuming it has the same annular Khovanov homology as this 4 braid, the first thing you can do is see like, oh, well, annular Khovanov homology detects braid closures, and it actually tells you the braid index. So we know that our link is the closure of some 4 braid. And so we want to study this 4 braid that it's the closure of and actually show like it should be conjugate to sigma 1, sigma 2, sigma 3. And you can use this nice relationship between annular Khovanov homology and Khovanov homology to actually check that the link you start with is an unknot, and so you know that this braid is a 4 braid that represents the unknot. And right, for the 3 braids, you can actually just stop there because there aren't many 3 braids that represent the unknot. But once you get into like 4 braids and higher, there's a fair number of braids that represent the unknot. So you need to work a little bit more than just knowing that you have a braid that represents the unknot. And so this is where that branch double cover construction is going to start allowing us to do things. We can use this spectral sequence, this relationship, to actually check that the knot homology of the lift of the braid axis in the branch double cover of beta is actually the same as the knot homology of the torus link T24. And then once we know that, we can actually check that we know that actually this link that we've built in the branch double cover is the torus link T24. Because we know that knot homology detects the torus link T24. And that's like pretty great. That's already a lot you've learned about this mystery link L, but we want to learn a little bit more. We want to be able to translate knowing this thing about the branch double cover back into knowing something about our braid. And so you have to work a little bit harder. We want to show that actually these braid closures are the same, not just that the links we build in the branch double cover are the same. And there's a few ways to do this, I think, but this is a way I really like. And you can make a version of this work for any of those other cases I mentioned. So one thing that's just true is that fibered links, if you've kind of picked how they should be fibering, if you're fibering them by cypher surfaces, they're determined by their monodromies up to conjugation. So we actually know that, and we know specifically because of how we built these fibered links that their monodromies are determined by the braids. So they're the braids under this Berman-Hilton correspondence. We look at the image of the braid. So we know that the image of beta under this group homomorphism, that's the Berman-Hilton correspondence, is actually conjugate to the image of this braid sigma 1, sigma 2, sigma 3. And we even know like the Berman-Hilton correspondence is injective, but that's not quite enough because you could think up lots of group homomorphisms that are injective that take non-conjugate things and send them to conjugate things. So you need to work a little bit more still. But in the case of 4 braids, we actually understand the Berman-Hilton correspondence very well. And it's just this map from the braid group on 4 strands to the braid group on 4 strands crossed with C. And so in this case, it's easy to see if things are conjugate after applying this map, they needed to be conjugate before applying that map too. And so you can see that this braid beta that we started with, that's representing our mystery link L, is actually conjugate to sigma 1, sigma 2, sigma 3. And so we know that our link L we started with really is the same as this braid closure here. And this part is like what I've written here on the screen for you is specific to 4 braids. So for those other braids I mentioned, you would need to give a slightly different argument, but it is possible to give an argument for the braids that we mentioned, or similar sorts of braids that being conjugate after the Berman-Hilton correspondence is the same as being conjugate before. At least what Fraser and I prove is that it's true for periodic braids, and all the braids that I mentioned before are periodic. And I'd be happy to talk about that later. I just didn't want to kind of get into too much of that in the proof sketch. I just wanted to mention it. It's possible for things that aren't 4 braids too. So I'm gonna shift a little bit and talk about a slightly different problem. So I wanted to, or a different question that you might approach with similar techniques. And so I wanted to pause here and see if there are any questions first. And I'll drink some water while I'm doing it. Okay, so then just to kind of keep going, like I think seeing this and seeing how you could prove that annular Khovanov homology detects all these braids, one thing you might be thinking is like, oh, this is really great. I'm just going to take any question I have about annular Khovanov homology, use this construction of building a link in the branch double cover, and translate my question into a question about not homology. And then I have all these tools at my disposal. And so I'll be able to prove like all sorts of things about annular Khovanov homology. So here's like another question you might have about annular Khovanov homology. And it actually predates annular Khovanov homology in some way. So back in the 90s, Hosta and Shizitsky had suggested that the annular variable for the Kaufman's gain bracket actually means something topologically. And then obviously, because that annular variable is related to the annular grading and annular Khovanov homology, you can also translate this into a question about annular Khovanov homology too. So they conjecture in 1995 that the highest non-zero annular degree is exactly the minimal intersection number of your annular link with a meridional disk. And I should say here, it's not too hard to show that this minimal intersection number is an upper bound on the degree. So the conjecture is really if they're equal, if that bound is sharp, always. And it's known to be true in some cases. So it's in their paper where they make this conjecture. Hosta and Shizitsky are able to show that it's true for links that have what's called a plus or minus adequately wrapped diagram. And it's certainly also known to be true for string link closures, which would include braid closures. The citation I know for that is this paper of Grigsby and Nee from 2014. It's possible it was known earlier, and if somebody knows that it was known earlier, I'd love to hear it. But I did ask both Shizitsky and Ellie, and neither of them knew of a different citation, though Ellie also seemed to believe that it was probably known before. So just like to give an example for this conjecture, just so we kind of understand what all the words mean a little bit, coming back to our example before of an annular link, if we look at a meridional disk for this disk would intersect our link in 2 different points. And that's actually a disk that intersects our link minimally. And this is reflected in the fact that if we look at its Kaufman's gain bracket, the highest degree for the annular variable is 2. And so this is an example where the conjecture is true. And we can see it's also true for annular Khovanov homology as well, that the highest annular degree is 2. And so this is somewhere where the intersection number agrees with this highest non-zero degree. And so it's somewhere where the conjecture holds. But this is what the conjecture is saying should always be true. That if you look at the minimal intersection number, it should be exactly the same as this highest non-zero annular degree. Either for the original conjecture says for the polynomial, and then a slightly weaker conjecture would just be, maybe it's just true for annular Khovanov homology. And this conjecture that it's true for annular Khovanov homology, it's a little bit weaker. Obviously, if it's true for the polynomial, it's also true for annular Khovanov homology. But you might hope that this conjecture for annular Khovanov homology is a little bit more tractable, just because you have more tools at your disposal. In the same sort of way, like to come back to the fact that Khovanov homology detects the unknot, whereas we still don't know if the Jones polynomial detects the unknot, even though that's been a conjecture for much longer. But you have a far less tools to be able to work with, so it's like much harder to prove. So you might hope that this weaker conjecture about the annular grading of annular Khovanov homology and how it relates to a minimal intersection number with the disk is somehow more tractable. And so keeping in mind what we just saw, I think a really natural thought would be like, okay, let's think about branchable covers and turn this into a question about floor homology. And then maybe we'll be able to use all sorts of tools that we knew about floor homology to be able to practice. So specifically, if we're starting to think about what happens and like how do things translate into the branchable cover, we know that the annular grading actually relates to the Alexander grading on not floor homology. And that seems really promising because something we do know is that the highest non-zero Alexander grading is recovering a Thurston norm from meridional surfaces. So we know that this Alexander grading is telling us about something about embedded surfaces and like how complicated they have to be. And we know it's related to this annular grading that we're kind of conjecturing should be about embedding disks and how many times they intersect, which you could interpret as being like how complicated are they in this perspective of the Thurston norm. So this seems really exciting. So like let's look at this idea. So coming here, as I mentioned before, we have this disk that intersects our link twice. And that disk does minimize the Thurston norm. But there's also another surface that also minimizes the Thurston norm. And I'm going to draw it for you here. There's this embedded torus that doesn't intersect our link at all. And this handle is going to follow this part of the link around. So we actually never intersect our link. And so we get an embedded torus. And both the disk and this embedded torus have the same Thurston norm. So this is somewhere where it's okay. We could use the branch double cover and check that the wrapping conjecture is true, or the conjecture is true for this example, which is pretty good. But let's look at another example. So here, now if we're looking at a disk, this disk all of a sudden, now it's intersecting our link in 4 points. But this disk doesn't minimize the Thurston norm anymore because there still is an embedded torus that we could find in the complement of this link, where now the handle for our embedded torus is actually going to follow these two parallel strands around. So it goes something like this. And again, it doesn't intersect our link anywhere. And so this torus does minimize the Thurston norm, but if you go and do the computation, this disk no longer minimizes the Thurston norm. And so we'd see this gap between what we'd expect is the highest non-zero annular grading for annular Khovanov homology versus the highest non-zero annular grading for not polar homology, because the Thurston norm is different from the minimal intersection number with an embedded disk. And this kind of continues. So here, I'm not going to go through drawing it, but there still is the same embedded torus in this picture. And now you could instead find that the minimal intersection number with the disk is 6. And I think at this point, like you probably could come up with like an example on your own where there's an embedded torus, so the Thurston norm is very small, but the minimal intersection with the disk is like 1,000 or 2 million or something like that. So you can construct these examples where there's an arbitrarily large gap between the Thurston norm and the minimal intersection number with the disk. And so you'd see this arbitrarily large gap between what's non-zero for a floor homology that sees the Thurston norm versus what should be non-zero if you believe the conjecture for annular Khovanov homology. And I should say here, like just as some history, those examples we just saw were kind of mentioned by Matt Hedden and Stefan Berley in 2010. Shortly after this approach to possibly proving that this wrapping conjecture about annular Khovanov homology using a branch double cover was suggested by Ellie Grigsby. And then I think people thought about it a little bit, but didn't have much more to say, and nothing was pursued at the time. But I think there was renewed interest in Floor homology and this wrapping conjecture after work of Gage in 2018 that was relating annular Khovanov homology to instanton floor homology. Specifically, I remember sitting in a seminar dinner where people were kind of talking about if his work just proved this wrapping conjecture again, and then people kind of came up with these examples that we saw before, again, kind of remembering them or coming up with them, being like, oh, well, it's not quite that simple. And in particular, like nobody knew if those examples I was just showing you, if the categorified wrapping conjecture is even true. So we didn't know, like, and if you don't believe the conjecture, these would be great places to look for a counterexample, because what's predicted by the conjecture looks very different from what's happening in any sort of floor theory. So if you think the conjecture is false, like these would be great places to look, because you see this huge gap between what should be the highest non-zero annular grading of annular Khovanov homology, which is like way up there, but the floor theories are just non-zero way down here because the Thurston norm stays the same. So seeing such a large gap might lead you to believe that those would be good candidates for as a counterexample. Sorry, my voice is a little bit sore, so anyway, I just wanted to apologize that my voice is a little bit sore. But it turns out actually that like none of those examples are counterexamples to the conjecture. And so I can show that there's these infinite families of annular links where the categorified wrapping conjecture is true, even though you see this really big gap between the minimal intersection number with a disk and the Thurston norm. So you can't just use this branch double cover or some other floor homology because they don't see what should be happening with the disks. And the exact statement of like what these families are is a little bit technical. It's in my paper. But I should just say it includes kind of that family that we were just looking at before. That's like a first natural example. And then I think this result's very, I mean, I'm kind of not sure always what to make of it, but I think it's very strange, but kind of interesting to see that there's this information that annular Khovanov homology seems to be picking up on that you can't see in not floor homology, the branch double cover. Or, and I guess I should say for experts, like everything I'm saying here is true kind of for, not just for the not floor homology of the branch double cover, but like any sort of floor theory of an annular link where it's detecting the Thurston norm. So that would also be things like annular not floor homology or an annular version of instanton floor homology as well. And so annular Khovanov homology is seeing something that like these other theories aren't really being able to pick up on. It's somehow specifically sensitive to disks rather than embedded surfaces, or at least that's what this seems to suggest. Which is a little bit strange, like it's somehow strange to be restricted to only thinking about disks rather than like embedding any surface you want. But it is interesting that it seems annular Khovanov homology really might be containing information about that. And so just kind of thinking about how we built those examples, we kind of had an example and then we were taking satellites of it or cables of it. And it turns out like you can always do something like that. So if you have some annular link and you have a surface that doesn't intersect that link, you'll be able to build lots of things like what we just saw that seem like they could possibly be counterexamples to this wrapping conjecture, because you take a cable of it, then the cable also won't intersect that surface, so the Thurston norm won't change. But your intersection with disks grows a lot larger if you take a large cable. You intersect n times as many as you did before. And so if n is big, that's like a lot bigger than what you started with. So, you don't need to restrict yourself to just cables here. You could think about doing other satellite operations, try and construct other possible counterexamples again, much in the same way that we did before. And here, I should say, like, something else was able to prove is just that at least some satellite operations can't be used for constructing new counterexamples for the categorified conjecture. So specifically, if you started with something where the categorified wrapping conjecture is true, and you do certain satellite operations, then you'll end with something where the categorified wrapping conjecture is true, even if you do this thing where you had these embedded surfaces so that the Thurston norm is staying constant, but the intersection with the disk is growing a lot. And the exact statement of like which operations you're allowed is again a little bit technical. It's written in my paper if you're curious. But I should say it includes cabling or any satellite operation where the pattern is the closure of a string link, more generally. And so just to give you like a quick idea of how I do this, I'm just trying to keep an eye on the time too. A key computational tool for doing this is extending the Batson seed link splitting spectral sequence into the thickened annulus. So Batson and seed have this link splitting spectral sequence in Khovanov homology that lets you relate the Khovanov homology of a link with the Khovanov homology of a split link built out of its components. And I needed to extend it to annular Khovanov homology. And I should say, like, it's not hard to do this. I knew you could do it for a while. I think other people knew you could do it too, but no one wrote it down because nobody like had a good idea of what to do with it. And like actually doing it is really just like, you look at what Batson and seed have done and you kind of write annular in a few places and do the same checks they do. And so it's not really hard to extend the Batson seed link splitting spectral sequence. But what's good about extending it is gives you this nice rank inequality where the rank of the annular Khovanov homology of your link ends up being bigger than or equal to the rank of an annular Khovanov homology of like the split link. So you're taking your link and you're pulling parts of the link apart from each other, which is like, we understand pretty well as some sort of tensor product. And so it's letting you take your complicated link and pull parts of it apart to make it simpler to study. And I think just to give you an idea of how you'd use it, I just want to give you like a short sketch where we could show that the categorified wrapping conjecture is true specifically for this link here. And this will give you like a good idea of how some of these other proofs go as well, I think. And we'll get to use this link splitting spectral sequence on the way. So if we're starting with this link, we know that there's this disk that intersects our link 4 times. So that gives us an upper bound on the maximal non-zero annular grading. We know that it's no bigger than 4, so we want to just show that it's also actually equal to 4. So we can just check that it's at least 4, because that's how numbers work, I guess, right? And so our first step in doing that is we're going to use our annular link splitting spectral sequence. We're going to pull the 2 components of our link apart, and we get something that looks like this, which is already a lot simpler and easier to work with. And then that rank inequality is just going to tell us that the highest non-zero annular gradient for the link we started with is at least as big as the highest non-zero annular gradient here. And then, like I said, this annular Khovanov homology we understand as like a tensor product. And a quick computation with the tensor products will tell us that the highest non-zero annular gradient for the link we started with is now at least twice as big as the highest non-zero annular gradient for this link here. And then this link is something where we can actually look at the branch double cover and see that for this link, using the branch double cover and not full homology, that the highest non-zero annular gradient has to be at least 2. Just because we know the Thurston norm of this, and we can kind of calculate through what that means for the annular gradient. It's a little annoying because you have to like renormalize between the Alexander gradient and the annular gradient, but it's not a big deal. It's just arithmetic. And then let's just like trace back what we've just shown. So we knew that this highest annular degree is at least 2, and we knew that for the link we started with, it was at least twice that. So that means that it's at least 4. And we already knew it was no bigger than 4. So we have something where we checked it's no bigger than 4 and also no smaller than 4. So we know that actually the highest non-zero annular gradient for this link is 4, which is exactly what the conjecture predicted. So we just have checked that the conjecture is true here. And I think seeing this is kind of like the key idea for how you could show any of those other results I was mentioning as well. So I know I'm getting close to 50 minutes, so I'm about to wrap up, and maybe I'll just end by kind of mentioning a very natural future question, which is like, you might ask, like, well, could you just prove the categorified wrapping conjecture? And I mean, that's an easy question to ask, but specifically, maybe like, let me suggest one way you might try and approach this question. One possible way to think about it would be that there's some minimal family of kind of generating annular links with respect to these satellite operations that we know can't build a new counterexample to the conjecture. So you might ask yourself, could you give a nice description of that minimal generating family, or even show that they all satisfy the categorified wrapping? Because if you show the conjecture is true for this family, and then you know that the satellite operations preserve the conjecture being true, then you know that the conjecture is true for every annular link. And the other thing you might ask is like, could you expand on this list of which satellite operations are you allowed to do that won't give you a new counterexample to the conjecture? And I guess I should just say that obviously, if the conjecture is true, then the answer is like every satellite operation. So you might think that would be like a good thing to just try and prove. But I should just point out that proving that every satellite operation preserves this conjecture, like doesn't give you a new counterexample, is exactly the same as proving the conjecture. Because if you're allowed to use any satellite operation you want, then actually your generating family of annular links is just like the one braid closure. Just that very simple core of the solid torus is enough to like everything is a satellite of that. And so if you knew every satellite operation would preserve this conjecture, that's the same as proving the conjecture. But with that being said, maybe I'll just thank you all for your time. Yeah, thank you.
Are there any questions for me? So I have one question. I guess maybe this is already, you were kind of mentioning this in your future questions, but when you looked at string links, I sort of think like that works really well with the Batson seed spectral sequence because you really do have multiple components. Have you thought about any classes where the satellited link is still a knot, like you go from a knot to a knot and you don't have any sort of like multiple components? Because that would sort of force your I mean, the torus picture is still going to be there, but the wrapping conjecture portion is less clear.
Yeah, it's a great question. And you're definitely right that you can't just use the link splitting spectral sequence in the same sort of way. If you are cabling with something that's giving you a knot back. I think the only thing I know of, which I think I've had written down in the paper, but maybe I can't remember, is there's like certain things you can do that I think I first learned, at least in the Host and Shizitsky paper that I cited. But there's certain diagrammatic arguments you could do. So like if you, for example, if you attach a braid onto the bottom of like something you already knew was going to work, then it will also work after you've stuck that braid on the bottom. And so you could like take something that's giving you a link that you already know and then like stick a braid on the bottom of it so that it becomes a knot when you close it up. And then you can do like some nice diagrammatic arguments. They'll let you kind of relate this new thing that's built a knot back to the thing you knew about that gave you like a link. But that's kind of the only situation I know of where I would still be able to kind of use some of these tools. I don't know if that's like makes sense or gives you like a nice answer to your question.
No, that's great. That gives me an example exactly.
Okay.
With string links. Yeah. Cool. Any other questions for me?
Yeah, where exactly is the Angular grading?
Could you hear that?
Yeah, I was gonna say I could only hear like maybe a little bit of that question. I'm sorry.
Do you want to hold up or do you want me to repeat it? Okay. I think if I remember what you said 5 seconds ago, where exactly does the annular grading come from? Is that right? Yeah.
Yeah, that's a great question. And it's definitely something I like didn't describe. But if you're familiar with kind of just the definition of Khovanov homology, where you're taking a link and then building a cube of resolutions, and then kind of building a vector space from that, you can think of the annular grading as just coming from now your cube of resolutions, instead of sitting on a plane, sits on a punctured plane, kind of because you want to remember where the core of your annulus was, or where you're, yeah, because you're working in an annulus. And so the annular grading is just going to count if your circles in your resolution wrap around the annulus or not. And if they do, then they'll contribute to the annular grading. And if they don't, then they won't contribute to the annular grading. Does that answer your question?
Yeah, thank you.
Okay.
Any other questions?
Maybe I have a question. This, I think it's just, I couldn't quite decide if this makes sense or not, but you know, you're working in a solid torus, basically thickened annulus. S1 cross D2, and you're asking about minimal numbers of intersections with point cross D2. If you work in S1 cross S2 instead, do those questions, the answers change? You know?
Yeah, it's a good question. I mean, I guess I'll first just say that I'm not super familiar with what's known about these questions in S1 cross S2, so I probably will miss a lot of things. And at least specifically thinking about Khovanov homology, like the version of Khovanov homology I know of for S1 cross S2 doesn't really have something like an annular grading on it that I was aware of from hearing people explain it to me. So I think specifically for Khovanov homology, people haven't thought about it. I do know some people have thought about kind of minimal intersection numbers with S2, these S2s and S1 cross S2, but I don't really like know much more than like it's something some people have thought about. So I'm sorry I can't give you a better answer than that. But I don't know if there was something more specific you were curious about or not.
Well, I was just trying to figure out, if it's known whether it's a radically different sort of question, or it's just, just compactifying that disk to a sphere is kind of trivial.
Yeah,
If it changes the whole picture, then that's information on it.
I'm not really sure if it's changes it a lot or not, to be honest with you.
All right, thanks.
Okay, let's thank Gage again. Here tomorrow morning. Well, okay, there's 9 o'clock breakfast and then 9:30 here tomorrow.
So I think you're